Now what do we got here? The normal distribution. Now, a lot of you have seen this, if not all of you, and we actually brushed on it just a couple of days ago. And now we are going to look very carefully at area underneath this. Now I understand that's a calculus idea, and there's some like integration or something that goes along with that, and but we don't need to do that. We have the numbers that are the areas under this curve available to us at all times. We want to know two things, though. We want to know, one, how to access those numbers, and two, if they are right on the standard deviation lines, we want to know what they are right away. We don't have to go searching for that. Like, for example, like right there on that line, we want to know exactly what that would be. Now, you'd want to look at this particular image and see a couple of things. The first thing you want to see is the three numbers that are on top, these three right here. And truncating them, you have 68, 95, and 99.7. And that is the name of a rule. It's called the 68, 95, 99.7 rule. Pretty simple little rule to name, or name to remember. It is the empirical rule of normal distributions. And it says that in between 1 and -1 standard deviations, so in other words, from here to here, 68% of the data can be found. Which then should probably bring up a couple of questions like, whoa, what do you mean data? What is that? Well, what is this graph? What is it showing? It's called the normal distribution. And like I said back at the beginning of the school year, don't sleep on this word distribution. What exactly is that word saying? It's saying all the observations shown graphically, distributed from low to high. Now this is a normal, and notice the n is capital, so that's the name of it, the normal distribution, in that it is a normal curve, a bell curve, and this normal curve theoretically extends and never actually touches the x-axis in both directions. Underneath this curve is area of 1, always. So it is a density curve since it's on this axis, and it has area equals 1. Okay, so then we've got 68% of the data there. It's quite a bit. It's 2/3. Then, at the second standard deviation line, so in other words, 2 standard deviations above, and there's above, right there, yeah, right there, and 2 standard deviations below, right there. In between those two lines, you have 95% of the data. So almost all of it is in between 2 standard deviations. You're virtually certain to be in between 2 standard deviations. In fact, if you're outside of 2 standard deviations, then you are potentially an outlier. And then what is outside 2 standard deviations? Well, then that would be 3 right here and here. And the amount that's in between positive 3 standard deviations and -3 standard deviations is 99.7%. So that really is all of it. 0.3 is not in between those two. So you are definitely an outlier if you're outside of those 2 lines right there. Now, also, if you notice inside the image that I have here, there's other percentages that then come up that you can figure out based off of this 68, 95, 99.7. And let's look at those percentages carefully. Take it right at, well, let's start in the middle. Let's not assume anything. Right here. What would be the percent of the graph that way from this middle line? Well, what is this middle line? It's the mean. It's also the median, and it also appears to be the mode. When you are on that middle line, this is a symmetric graph, so that would be 50%. Both directions. 50% both ways there. At the mean line right here. But what about the 1 standard deviation line? What if I were right on that, and instead of being interested in between 1 and -1, now I'm just simply interested in above 1? How much would that be? Well, how am I going to go about figuring that out? I know I've got 68% from here to here, and I know it's 50% this way, and I know it's 50% this way. And I know the graph is, that tells me, therefore, the graph is symmetric. And if the graph is symmetric, then as this image is indicating to you, there's the same amount of that 68% on either side of that 50% line, which means there's 34% from the middle line, the mean, to the 1 standard deviation line, and in the other direction as well. That's also 34%. So how does this help me then? Well, if I know this 50% this way, and I know of that 50%, 34% of it is right there, then from this line, which is the end of that 34%, this way is going to be 54 minus 30, because that's all that's left, 16%. And keep in mind, with the exception of the 50, these are all approximations. So 16% is at and above 1 standard deviation, making at and below 1 standard deviation above 84%, since it adds up to 1. Okay, probably the trickiest one to find, and that works also in the other direction. If you let me clear this ink, that if I'm right here, then there's 16% below 1 standard deviation, making 84 above 1 standard deviation below the mean. Ooh, I drew that in the wrong spot, I'm sorry. I meant to draw that right there. That's the 1 standard deviation line. Get rid of that. Sorry about that. So reboot on that. 84% above 1 standard deviation below the mean. 16% below 1 standard deviation less than the mean, that number right there. 1 less. And then what about the 2 and 3? Well, let's answer this question right here. Look at the green arrows I've just drawn. We know in between the 2 green arrows I drew that there is 95% of the data. That's part of the 68, 95, 99.7 rule. Which means, since the area underneath the curve is 1, outside of the green arrows, outside of the 2 standard deviations, so less than 2 standard deviations below and more than 2 standard deviations above the mean, is a total of 5%. And we know the graph is symmetric, 50% of it's that way, 50% of it's that way. So then that tells me that if I just divide the 5% by 2, that's going to be how much is this way and how much is going to be this way. And in fact, that will be accurate. So there's 2.5% below 2 standard deviations below the mean, and there's 2.5% of the graph above 2 standard deviations above the mean. And then the same idea works for 3 standard deviations. So we'll draw the line here, you draw the line here, and you're interested in above and above, and the question is then asked of you, how much is in between those 2 blue lines? Well, that's 99.7%. Leaving on the outside is 0.3, meaning 0.15, and don't forget the point, 0.15%. So 1/10 of 1% basically, and 1/10 of 1%, 0.15%, is on the outsides of those 2 blue lines, above and below, 3 standard deviations above and below the mean. And then that's utilizing the 68, 95, 99.7 rule. Now hopefully when you look at that you say, okay, no problem. That seems like a lot to remember, but I guess if I have it all written down, then no big deal. But what if I'm not on one of those standard deviation lines, which is a legitimate question? What if, perchance, for whatever reason, I'm just off it with whatever data that I'm holding? Like, say, my data landed right about, ooh, there. Wait, let me get the thing to right. About there-ish. Where now, I'm not on one of those standard deviation lines. Well, then how can I find the area? I can kind of approximate it, but it's going to be hard because if I'm asked to find all this, this shape's not a rectangle. I can't do any, like, proportional. That's just simply not going to work. So how am I going to do this? Well, there's a nice little pretty formula for us to use. It's actually one of the easier formulas to use as long as you know what it is that you're reading when you read it. So let's take a look at that. Let's just look at one of these nice and blank. And we know that it's a normal distribution, so we know that this line going up the middle here is the mean. Let's call it the mu. And let's say I've got a value that's somewhere over here. In fact, let's do a little context to this. Let's say this graph that I'm showing here is the distribution of the heights of young men across the United States. Men aged 18 to 24, let's say. And we know, let's say that this is a known, we know that the mu is 70. It's a pretty easy number to work with. So the typical height, American male, aged 18 to 24, is 70 inches tall. And we know, let's say this is also a known, that the standard deviation, and there's that little symbol again, that's the standard deviation underneath one of these things, is, let's say, 3.5. So on average, men range 3.5 inches tall from 70. And the value that I've drawn in a blue line right here is 72.5. So it's less than one standard deviation. I probably should have drawn it a little bit that way, but whatever. It's less than one standard deviation. But exactly where is this? How do I find this? Well, what I need to do, and please don't lose sight of this word, I need to standardize my values. I need to make my values all become onto the same normal distribution graph. So in other words, I need to make it so that the values that I'm dealing with are irrelevant, and what I'm actually dealing with is a standardized value. And that's actually called a z-score. I'm going to find a z-score. So what is this z-score? Well, the z-score is the exact number of standard deviations you are with your observation from the mean in the context of your problem. So, in order for me to find that, in order for me to make that, in order for me to standardize this, what I need to do is I need to take my specific value, which in this case is 72.5. And then I need to find the difference of that and the mean. And then I need to divide that difference by the actual standard deviation. Now, if you take a quick glance at this and pretend instead of me saying 72.5, I said 73.5 in my value right here, you probably would have quickly said to me, well, that's exactly one standard deviation because it says it right there. That's one standard deviation. So go ahead and throw that into that formula and see what happens. And in fact, 73.5 minus 70 over the standard deviation would equal 3.5 over 3.5, which does indeed equal 1. So what you're doing is you're standardizing this. You're standardizing it to a graph where this line is just simply the 0 line, and these standard deviations are the values of 1, 2, and 3 above, -1, -2, -3 below. That's what standardizing is doing. You're making the mean 0 and the standard deviation 1. So now our value right here, we get 2.5 over 3.5, which is a little less than 1, and in fact, it equals, according to my calculator, 0.7142, so I'll just say 0.714. Seems far enough. Well, now what? Now I know what I already knew. I'm a little less than one standard deviation above the mean with my 72.5. I could tell just by comparing. And I guess I'm one up on a little, like I know I'm approximately 1. I know exactly what it is. I know it's 0.7 of 1. but what do I do with this? Like, how then can I handle this? Well, this is where the integration would come in if it's calculus, to figure out how much is there. Because like I said earlier, by earlier I mean last week, if you're in a continuous density curve and you're on some individual spot, you can't figure out the probability of being on that spot because there's an infinite amount of numbers underneath the density curve. All you can do is figure out a range. So if I'm asked, instead of me saying, what's the probability I'm here, I say, what's the probability I'm at least 72.5 inches tall, or the randomly chosen person is, I should say. Okay, now this is something I can figure out. Now here's an area for me. I've got everything from 0.7 standard deviations above the mean and above. Now there's two ways for me to gather this data. The first way, I just quite simply look it up. The Table A chart is provided to all students of statistics. Table A shows every single z-score value from 3.5 standard deviations below the mean to 3.5 standard deviations above the mean. It shows all the areas at those points. So what does this look like? Yeah, it looks like this. So let's take a close look at this. This is going to look a little bit confusing at first, but it is just a chart. It is just a find your number and go. The first thing you have to identify when you look at this chart is what it says on the bottom right here. It says, note that the probabilities given in this table represent the area to the left of the z-score. To the left of the z-score. So wherever your z-score is, to the left of it. That's what the numbers represent, and the numbers are probabilities or areas. And that's key to this. You got to make sure never lose sight of that. What you're looking at here are to the left. Now that doesn't mean that doesn't tell you what's to the right, because you know it adds up to 1. And so if it adds up to 1 and it's giving you to the left and you needed to the right, well then you just find that to the left and you subtract it from 1. Simple enough. So let's find our number. Our number was if I'm not mistaken, 714. I need to find this number on here. Well, I'm less than 1. So let's try to increase the size of this chart so we can see it. There we go. Now I'm focusing in on what I know we're going to be dealing with. Here's a z-score for us, right there. It's a z. And then these are all going down, potential scores, all the way up to, like I said, almost 3.5. 3.4. You have to find yours. Well, ours was, again, 0.714. So where is that? Well, here's 1 flat right there. That's 1. That's not the one we're dealing with. We're dealing with less than that. We're at 0.7. And that's right there is 0.7. But it wasn't just 0.7, it was 0.714. And that's where this massive numbers comes into play. Is now you have to find specifically 714. So how am I going to find that? Well, look at the top row up here, these numbers. Those numbers are your next decimal places. So I had 714. So I have 0.71 right there, and 4, which is going to be somewhere in between 1 and 2. So you see how I got that 1? 0.714. You can match the 1 to the decimal place of that one right there. So our number that we're going to be interested in is in between 0.7611 and 0.7642. And in fact, just saying 0.7611 off this chart would be sufficient. So what is that number then? Well, now go back to, and let me see if I can just tiny up this thing real tiny. Let's get it out of the way. Go back to this now, and we wanted to know how much was above 0.714. And then we learned in this chart right here that it was approximately 76%. So take that in for a second. That's what that number said right there. We'll just go with that one, 76.1%. So we can go ahead and round that off to 76 for now. So 76% was what? 76% was, fix that, this way is 76%. So then how much is this way? 1 minus 0.76, leaving us with 0.24. So 24% of young men aged 18 to 24 are 72.5 inches tall or more. Not just 72.5 inches tall, but 72.5 inches tall or more. 24%. That is using the table. Now you might say to yourself, okay, it's a lot of talk, a lot of back and forth, but ultimately that wasn't too bad. It was a little tricky with finding the number on that, and let's go ahead and put this back up on the screen again if I can get my fingers on it. There we go. And I'm missing it again. But there we go. But let's say I had to find what's the probability I'm at or below. So kind of looking like this over here, if you look at the top of the screen, that I'm at or below 2.3 standard deviations. Exactly, just 2.3, no other decimals there. So then I'd go to the z-chart, I'd find 2.3, which is right there, and I'd just look at the very first number, because that very first number is 2.3, and that's it, 0.0107. So in other words, 1% of the data is at and below 2.3 standard deviations below. And that also tells me that if I wanted to be above, 2.3 above, so I'll go to where that is. There it is right there. 2.3 above is now 0.9893. And in fact, the two numbers will add to 1 because it's symmetric. So if I am 2.3 standard deviations below and I find 1% and change, then if I go to 2.3 standard deviations above, that's going to tell me 98% and change because the two numbers are going to add up to equal 1. All right, and that is using Table A. This table is always at your disposal. It is never something you have to go look for or ask for. This is something that you have with you. This isn't a I'm being convenient and giving you something. This is there for you always when you're dealing with statistics. And that's something to keep in mind. Now, because of that, there is another way to go about gathering this information, and that is by using your TI-83. So now the next part of this that I'm going to go over with you, you're probably going to want to have your TI-83 in your hand with you while you do this. I don't think that this particular program is going to allow for me to do any kind of physical demonstration for you. So get your TI-83, get it in your hand, and we're going to walk through using your calculator, which is actually the preferred method. All right, so here we go. We have a nice little Google image of a TI calculator, and I'm going to focus your eyes on a button that you're going to use a lot the rest of the year, and it is right there. It says VARS, and right above VARS it says DISTR, and the DISTR is where we're going to go. That is distribution. Now there's a good 1, 2, 3, 4, 5, 6, 7, maybe even 8 things inside this list that you're going to use with me. So this is something you want to be familiar with. You don't want to get caught on, like when I say find the area of the binomial or geometric distribution and you don't even know where to start. You want to make sure this is where you are. You are good with this. You are going to VARS. You're going to the distribution function on the calculator. So again, second VARS is where we're going to go. Now when you hit second VARS on your calculator, what should then come up is this on your screen. Let me put it right there. Now I understand some of you's calculator might look like this in a second, so let me get this available right there. But to start, it's going to look like this one. This is the one you're going to see. Now you got a couple of choices here right off the bat. And the first thing says normal PDF, and the next one says normal CDF. I'd like you to make a mental right now this. Just pretend it's not there. Normal PDF is not something you're going to use with me ever. It's not going to come up. So pretend you don't even see it. What you are going to use, though, is normal CDF. This is the one we're going to hit. So if you hit that normal PDF, this will not work out for you. Normal CDF will. Maybe you're asking yourself, what does the CDF stand for? Well, the C is cumulative. The D is distribution, or distributive. And the F is function. And what is it going to give you? It's going to give you the area under a normal curve, hence the normal part of that. So what it'll tell you is if you give it the necessary information, it'll tell you what area is in between what you tell it under a normal curve. Okay? So now, when you hit enter on this normal CDF, you're going to see one of two things. You're either going to see it come up where you have just this, which will not go on top, unfortunately, whatever, right here, except there won't be any writing. There won't be any 65, 80, 70. It'll just say normal CDF. Or you're going to see this one right here. And this is if you have a newer calculator. This is what it looks like. Okay? So now what? Well, when you have your normal CDF, what it's asking you to do is give it some parameters for the normal curve. So I'll draw the normal curve right here. The normal CDF wants you to tell it between what two z-scores do you want the area of. So from here to, say, here is what I want. Now I need to know what those z-scores are for that. So let's say this was negative 2.3 and this was positive 0.85. I'd like you to real quick do that on your TI-83, 84, whatever you're holding. I will too. You go second vars and go to distribute, go down to normal CDF1 down there and just simply type negative 2.3 and then comma, make sure you put that comma in there, 0.85. And now you're asking the calculator to give you the area, all of this. And this is exactly the same as looking it up on the chart. You can do this by looking it up on table A. But tell me, calculator, the area between those two lines. Now, if you did this correctly, if you typed negative 2.3 comma 0.85, then you got 0.7916. So in other words, in between those two z-scores is 79% of the graph. And that's what the normal CDF told you. You got to make sure you put that comma in, and you have to make sure you put the low number in first before the comma, the high number in next. And then it'll tell you in between the two. Now let's say your screen looked like this over here. Well, if that were the case, then what you would have done then is for the lower, you would have wrote right here negative 2.3. For the upper, you would have written 0.85. But then now what? What do I do with these two numbers? Now, because the numbers I put in here and here were z-scores, that means that I had standardized whatever it was that I was measuring, whatever heights, weights, whatever it was that I was looking at. I'd already found z-scores for my data, and I now had the standardized scores. Now, if you recall, when I told you you standardize something, you're making the mu 0 and the standard deviation 1. And that's exactly what you would write here and here. You would write 0 for the mu and 1 for the standard deviation. And then you just simply hit paste. And if I'm not mistaken, then it would change from this, which I'm not going to be able to grab now, this screen to now this one that's right here. It'll look like this. Okay, now, let me go back to this one right here. And when you look at this, you might say to yourself, well, wait a minute, what's going on here? There's 1, 2, 3, 4 numbers typed into this one. And this is another interesting thing. What I just told you in what is now been minimized over here I told you that you can put in the two z-scores, the low and the high, for normal CDF, and I'll tell you the area in between. You actually don't even have to get the z-scores. You can use your actual data. And if you type in from your actual data, so let's say we had this right here, and let's just use the numbers that I've got available for me. So this appears to be asking for something along the lines of this. And the area it wants is like right here. Might be a little more. Here's what this thing says. This says, find me the area, O calculator, between 65 and 80 if the mean is 70 and the standard deviation is 4.5. And so that's what I drew over here. On this graph, I got 80, I got 70 was the mean, and 65 was the low number. So I guess this blue line should be a little more to the right, whatever. And I want the area in between, knowing that the standard deviation is 4.5. So you can write low value, high value, mean, standard deviation. And the calculator will also do that area for you. So in normal CDF, it's always a C, you type in low Z, comma high Z, or, get rid of this, if you don't feel like getting the z-scores, which shouldn't be that much of an issue for you, but that's okay, then you type in to normal CDF, low value, high value, comma, mean, comma, standard deviation. And then that's how you get your area under the curve without looking it up on table B. This is my preferred method. If you ask me to find area under a curve and I have a TI 8384 at my disposal, I will do that. That's the way I'll do it. I find that to be much, much easier than looking up at a chart. The chart had piles of numbers to sift through. Very simple to make a mistake on. You'll mark up because that's the way you'll find the number most likely. And so using normal CDF is easier. Now maybe some of you also said to yourself, wait a minute, what if the problem that I'm dealing with is one in which I have to find not in between two z-score lines, but I have to find from, let's say, here to basically infinity below it. Well, now what do I do? Pretty simple. You just have to give a low point and a high point of a z-score. So if I know the z-score is, let's say, negative 0.92, as it is right there, then what I'm going to do is I'm going to put in a low and a high in normal CDF z-score. So for my low, I'm going to type just a gigantically large negative number. So the calculator image right here has negative 99999. Perfectly fine. That's 99,999 z-scores. Or the z-score of that, I should say. That's humongous. That's way down there, and that's perfectly fine. Just has to be a humongously large negative number. Comma, negative 0.92, which was in fact my high value right here, because I wanted everything this way. And that's it. You just simply type in something to that effect. You can use negative 100,000, negative 1 million. As long as you've got a large number, you are perfectly fine. But do indeed make sure when you do that, you're using the z-scores, because if you're just using the context of the problem, like I did in the second example I showed you with this calculator function, your number might not be large enough. So make sure that you are indeed using z-scores in that case. Now if you look at this example right here, let me get this one minimized and out of the way so we can look at this one. This is on the other screen, which I don't know. There we go. When you look at this one, they've got this number written right here, Anybody familiar with the TI-8384 would know that this is the largest number you can type in the calculator will still operate. So you can use that as well if you want. But if you look at that and it doesn't look like it makes any sense to you, then just type negative 99,999. It's fine. You don't have to type this infinity number. It's not going to be any different in the end result of your answer. And same if you are dealing with a value that's on the high end, you're going from here to infinity in the other direction, so you want all of this, then you could just write that number without the negative, or positive 99,999. And remember, when you are dealing with this, that would be 0, and that would be 1, because you've standardized your scores. Okay, now another thing to look at in this distribution function, which is second vars, and we will use right now, is this one. Inverse norm is what this says. Inverse norm is when you know the area and you need the corresponding z-score. So now it's kind of the backwards. When it's normal CDF, when it was that one, you knew the z-scores and you needed to find the area underneath. Now in inverse norm, you know the area. Now you want to know the z-score that matches it. Because you could also do that on table B if you think about that. If I told you what z-score corresponds to area to the left of it, 0.35, you could find in that big giant mass of numbers of table A, 0.35, and then match it to the z-score that's there, or at least the closest number to 2.35. Now inverse norm will just simply do this for you. So let's take a good look at inverse norm. Minimize this, and this one right here. And what is it saying? This says inverse norm 0.25. So what it's saying to me is I have a normal distribution, and what I'm interested in is what is the matching z-score where 25% of the graph is at and below what I've typed. Now I typed 0.25, so that's going to be somewhere in here. And this is going to be 25% of the graph, all over here, and I need the corresponding z-score. And so all I do is type that in, and then it just quickly tells me negative 0.767, let's say 5. So negative 0.675. Now, does that make sense to me? It should, as the mean and one standard deviation would be here, and I've already learned today that 16% of the graph is at and below one standard deviation, and I was asking for 25%, so it's got to be less than one standard deviation below, and in fact it is at negative 0.675. And that is using inverse norm. And then you could also, if you had wanted to know the opposite of that, if you had wanted to know all of this from there, then instead of typing inverse norm, you would have gone to normal CDF. And so now we got it. We know where to go to figure out all this stuff. We know second vars on our calculator brings us to the distribution function, and we find in our distribution function normal CDF, and normal CDF tells us the area under the curve, and it might look like this, it might look like this, but either way we type in our low and high z-scores, and if that's the case, then that means the mu is 1 and the standard deviation is 0, and it'll tell us the area under the curve. Or we could type in all four values being in context our low value, our high value that we're interested in, the mean of our data, and the standard deviation of our data with commas in between all four of them. And then if we want to the ends of the infinite curve, then we just type in a gigantically large negative number or positive number, depending on which end. And then if we need some sort of actual z-score to match a proportion or a probability or a percentile, then we type in inverse norm, which is found in second vars. And in inverse norm, it'll tell us the corresponding z-score to the proportion that we've written in, remembering that when you do that, it is the area, wherever you type that score, to the left in inverse norm. And there you go. That is z-scores, standardized scores, area under the normal distribution. And like I said before, this is tattooed to our bodies and not going away. We will use this stuff a lot.